Hello everybody, good afternoon. Today I will talk about the low power RFIC design, and primarily I will cover the very basics or fundamentals needed for the RFIC and its applications. And first of all, you should know that why you want the RFIC design, because almost everywhere you will find a wireless on your cell phone or sensors or any handheld device. The latest trends make it wireless, and the RF front end is the most important, the basic components for any handheld or any RF devices. Therefore, design of RF circuits is an essential part. And secondly, why you want to make it low power? Because battery life is important. Suppose I want to design a system which will include a sensor, and that can work for 5 years with the same battery, and the battery will work at 1 volt, then you can have an excellent market, because almost these sensors can be thrown in anywhere and it can detect the signals and transmit to the nearest satellite or some other system, and you can also have a close monitoring systems. Therefore, the RF transmissions and receiving is a major research domain, especially low power in the VLSI. Why VLSI? Because so far we are working on the realization of RF components by realizing some discrete components over a board. We call on-board or PCB. You are integrating those components. But if you want to make the whole chip together to make a single chip solutions, that will be area wise, it will take less area, it will cost less, and it will power will be less. So that is the motivations behind this work, that why we will actually learn the low power IC design. And I will also talk about the very basic part of RF IC design. So before you go into the RF design, you should know a very fast we can go around the various frequency range. So if you look at that frequency range from say 100 megahertz to 10 gigahertz, that is the range which is known as the RF band. All your cell phone applications, you know that for GSM, it is 950 megahertz, the center frequency with 26 megahertz bandwidth like that. Or for your Bluetooth connections, it is 2.4 gigahertz. Or for WLAN connection, it is around 6.3 or 5.6 gigahertz. So roughly you can say that from say 100 megahertz, because you know that the online video streaming, now it is the the DVB-H for handheld cell phone that will also provide you the video. Then the kind of frequency range is around 472 to 670 megahertz. So from 100 megahertz roughly from the lower range and up to 10 gigahertz is the domain of the RF. And above RF, it is the microwave and the millimeter wave regions. And design of these RF circuits in that frequency range is quite challenging, because it was initially thought of doing all the high frequency stuff using exotic process like say gallium arsenide based or some group 3 compound based IC, which will expensive. But now even silicon, the cutoff frequency can go up to 100 gigahertz. So it is now possible to realize even silicon based RF circuits. So whatever we will talk today or we will learn today is basically a very cost effective silicon based RFIC design, or more precisely it is RF CMOS. That is, we will use the same digital CMOS process which can be used for digital circuit design, can also be implemented for fabricating an RFIC. What is the advantage of that? That you can have large amount of digital processing along with your RF front. Together you can have a single chip solution or SoC. Therefore, the challenges of today is to implement the low power RF circuits using the standard digital CMOS process without going into the exotic process to make the cost less and less. Now, if you look at the first challenge, if you look from the conventional ideas, people will say that, okay, you are working with RF domain where the basic analog concepts, lump parameter models is bound to fail there, because you know that all distributed parameters, you have large parasitics. And so which law? Because all you already know from your analog course and basic electronics that it depends upon all your circuits is finally obeying the Kirchhoff's law, because it is the AC small signal analysis, right? Where the assumption is, if you look at even the exponential devices, suppose transistors or square devices, is actually, this is called your first order, you taking the first order approximations, and you are only considering the signals which is very low, that is low or small signal, and the frequency is not so high. Then your lump parameter model is valid when the lambda is very, very high compared to the component size. But what happens when the frequency goes up in the gigahertz range? Then the wavelength goes down, and when it is comparable to the size of the components, then you know that there will be a lot of reflections, there will be a lot of mismatch, because of the ultimately you will find there is a phase difference along the length of the component, and that creates the challenge that whether the Kirchhoff's law is still valid or not. So first thing you have to know, very fundamentals, whether our KCL and KVL is valid in RFIC design or not. Otherwise we have to really go into the Maxwell equations and solving all the electromagnetic equations for designing the RFIC. But thanks God that world is not so complex, so under certain circumstances we can really use this standard KCL KVL even for RFIC design. So what is the logic behind it? Let's go into that. Before going into this paradox, whether the Kirchhoff's law is still valid or we have to go for Maxwell law, let's charge ourselves with what are the possible applications in these areas. So wireless communications, probably you know very well, everywhere it's wireless communications, right? Mobile phone or for even video broadcasting, wireless communication is a major use. All the front end, you know that after the antenna, the major part is known as the RF front end. And then after the signals at high frequency gets down converted, and then it is digitized, and then into domain of the digital signal processing, or more or less we call it is a baseband process. But this RF front end catching the signal at high frequency, it is in the analog RF domain. So there is no solution, easy solution that you can solve this by digital process, because suppose 2.45 gigahertz signal feeding to an ADC, if you think that way, and that converts finally to digital signals, and then everything will be digital signal processing, is not so simple, because that high conversion rate ADC 2.45 gigahertz power consumption, and that is ADC is challenges, very, very challenging to design that one. So the basic thing, you have to catch the signals at high frequency by the analog front end or RF front end, and then down convert it to the baseband, and then you process for digital or further processing for the baseband. So that's why it is omnipresent in everywhere, in your cell phone or wherever, any application in the wireless, you will find the RF front end. So that's why the motivations to that. So you will find anywhere, the radar, navigation, remote sensing, RFID, RF tag, then automobile and highways, anti-collision devices, and for say tire pressure sensors, and largely is sensor applications. People are miniaturizing the sensors from some macro domain to micro domain. Now the sizes of the sensors is say 200 micron into 200 micron, or 40 micron into 40 micron, which is called namespace sensors. Okay, you are having the same effects in the macro domain by scaling down its size to micro domain. But if you still use the conventional cable to connect or get the signal or access the signal, then the very purpose of the miniaturization fails, right? So what is the next options? To make the signal conditioning circuits as well as the RF and RF transceivers included in the sensors. That's why the whole domain is known as the smart sensors. Smart sensors means where it includes the sensing part, the transaction part, then the signal conditioning part, and then finally the transmitter and the receiving part together. So you can have an actuators, you can have a sensors all together to make a single chip or say 2 chip or 3 chip solutions. So, and there is a huge amount of applications coming up in the medical areas. People are now putting the devices in vivo inside the body. How to power up the devices inside the body? You cannot think of putting a brain mapping system inside your skull and having a battery. If you cannot think of a system that is a doser which can minuscule dosing of say some medicine is possible, but without powering by battery. It should be done by RF linkage. We call RF telemetry. That is, the devices will be inside your body, and then it will be powered and controlled by the RF telemetry. Wherever you will find the omnipresence of these RF applications. And radio astronomy is the amazing field where really to detect the signals is a challenge, radar and then signal processing. So these are all in the domain of the RF, and low power RFIC design is the most challenging part to make a consumer base in the wireless domain. So now coming back to this earlier statement, very fundamentals, whether my Kirchhoff's law is valid or not, or whether the Maxwell equation will be the king of RFIC design. So let us make a vis-a-vis study. These are the 4 Maxwell equations. Divergence of E equal to rho by epsilon 0. Divergence of B equal to 0 is monopole cannot exist. Then curl of H equal to epsilon del E del T plus J. And curl of E equal to minus mu del H del T. So these are the 4 Maxwell equations. If you look at the other side, the Kirchhoff's law. Now, suppose that the velocity of the electromagnetic wave in a media is what? 1 by root over of epsilon into mu, where epsilon is the dielectric constant and mu is the permeability. Now think of a situation that C is infinite, very, very large. Then under what circumstances she would be very high? Either mu will tend to 0 or epsilon will tend to 0. It's a theoretical concept. I don't think any materials exist where dielectric constant is 0 and mu is 0. But we can think of very low, tending towards 0. That means your velocity, that is propagation, electromagnetic propagations, velocity is reaching the infinite value. That's exactly happening while you're designing encounter the IC design. And if you look at, if you take either the equation 3rd and the 4th, and you apply epsilon equal to 0, that is curl of H equal to 0, then what you find? A curl of H equal to J, then what you find? You take the divergence of J equal to divergence of curl of H. What is the divergence of curl of H? Vector, it is 0. What is the divergence of J equal to 0? Simple Kirchhoff's current law. That is, at any node, the total amount of current entering is equal to the outgoing current. There is no sink or source in the systems. So I can jolly well find out the Kirchhoff's law from the Maxwell equation under special circumstances. What is this special circumstances? That the propagation is very, very high speed in the system. If you look at the equation 4, that is the curl of E equal to mu del H del T, and also you put mu equal to 0, then you can immediately find out that line integral of this E, that is electric field, along say along a closed path is what? Again 0. What does it mean? That is voltage. If you sum up the voltage around the loop, what is that? Equal to 0. What is that? It is Kirchhoff's voltage law. So if you can derive or if you can interpret the Kirchhoff's law and the voltage law from the Maxwell equations, then apparent contradiction can be avoided. Two fundamental laws, they are not fighting each other because they are expressing the same physical principle, and we can establish it very thoroughly. Therefore, look at now the practical case. Suppose I want to design something like at say 1 gigahertz frequency, 950 megahertz is your standard GSM mobile phone, okay, and then you approximately take it as 1 gigahertz. What is the equivalent wavelength of 1 gigahertz? 30 centimeter, okay. Now the wavelength is 30 centimeter. Now if you have the dielectric constant, it is in wavelength in where? In space, okay. But if it is, what is the dielectric constant? What is the media here? The silicon, because you are realizing the CMOS circuit for the RF design. So what is the dielectric constant of that? Around 10.7. So take it as 10. Then what will be my equivalent lambda? Is 3 centimeter. Now there is an assumption that when the lump parameter fails, when the component size is 1/10 of that lambda, that means 3 millimeter. If it is 3 millimeter, if the component size, okay, then you can think of going to the distributed model or transmission line model, or you have to apply the electromagnetic solutions from Maxwell equations. But what is the dimension of today's devices? Can you think of it? When we have started say 10 years back, my first RFIC design was used by 0.25 micron technology. Now my students are working with 65 nanometer technology, and they still say are not very happy with that. They say, sir, now I have to work on 45 nanometer technology. Oh my God, think of the device geometry and the size, and it is 3 millimeter for 10 gigahertz, 1 gigahertz. So component size is much smaller than the wavelength. So we can jolly well can assume the Kashyap's law. No confusions. We established that Kashyap's law can be used for RFIC because our component size is pretty low. Now the components are not standalone. Those components are to be connected by inductor, capacitor, interconnects. But those inductors, capacitors have got more values in the dimensions, not in micro domain, micrometer, they may be millimeter. Then you have to apply the Kashyap's law, the Maxwell equations. So it's a combined analysis is required for circuit analysis. Both the Maxwell equation mostly for the passive components, and the active components you can use the small signal high frequency AC model for your RFIC design. That is in the nutshell that what is the scenario of RFIC design, that still the small signal high frequency AC design is valid for RFIC as long as our component size is very small compared to the wavelength of the operating frequency. Now come to the next slide. We should know a little bit about what will happen if the frequency is very high or the component size is very high compared to the wavelength. Then a conductor, a simple conductor would not be a pure conductor. Then it will be a basically LC ladder network. It's called transmission lines, because and where is not a simple resistance. It has got an inductor as well as a capacitor, and it will have a ladder. It's a series of that LC network that constitutes your wear. Think of the complexity of the problem, because this tells you that suppose you have a simple wear and you are giving an AC signal. Have you ever thought of that if the frequency is A sin omega t, then my output will be not B sin omega t or B cos omega t? You will always assume that my frequency is unchanged because it is a simple wear. But in case of lump parameter or distributed, or where the transmission line modes, that when the component size is comparable to the wavelength, then what happens? You may not get the straight way the output with the same frequency. There will be a spectral response to that. You will find that it will act like a LC filter. So there is a frequency response beyond which your signal will drop down, or after or below a certain frequency there is no signal. So all this will come because of these effects. For example, a capacitor. A capacitor is not a simple capacitor. It has got a series resistance like a loss in the capacitors and a leakage path Rp, and also another parasitic capacitance. So the model of the simple components become more and more complicated when you go for high frequency, that is comparable component size with the wavelength. For example, the resistor. Resistor has got an inductor as well as a capacitor. An inductor, a simple inductor, is not an L, but it constitutes also a resistance in series and capacitor in parallel. So you know that while you will be modeling those components, you have to take care of that additional parasitic components. That is the major challenges of RF design. That not so simple or innocent component, they have certain parasitics, they have certain models that you have to include to take its real effects of introducing those passive components. This is one challenge in the system. So now you know that you are in the background, you have a little bit of background of analog design. So let's try to figure out what additional ideas you need or care you need to extend from analog design to RF design. So you must have learned about that in analog design is primarily small signal AC equivalent circuit. That's true. You have used all the small analog designs for common emitter amplifier or common source applications. You have used the G pi model, right? So you have used the small signal AC model. Okay. Then you have talked about the linearity of the systems, that is compared to the input signal levels, up to what extent the devices are linear. Then we talked about for oscillator, what is the stability of the system, even for amplifier, whether the system is going to be stable or unstable. Then noise, this is the most important, is of paramount interest in circuit design, that how to interpret the noise. Basically, what are the sources of noise, first you have to diagnose, and then you have to solve that, how to reduce the noise. Because you have to detect the signals out of a noisy platform, and signal to noise ratio should be high enough so that you can detect some appreciable signals to get some informations out of it. So noise model vis-a-vis the origin of the noise, the theory behind it should be done very, very strongly. So these are the A, B, C, D, the 4 components: linearity, small signal model, stability of the noise are the prime key factor of analog design. But vis-a-vis if you look at the RF design, along with these 4, there are other 2 components or 3 components are coming. One is matching. Matching means you know only one matching case, that when the source resistance equal to the load resistance and maximum power is transformed, right? They are in conjugate matching. But here the matching means something else. That means the S parameter or the scattering parameters, you have to study that when you actually increase the frequency of your input signal, then your passive components are no longer acts like a lump parameters. They have a distributed parameters, like they have a resistance, have a capacitor, as I explained, or inductor have a resistance and a capacitors. So they will form a complex network. And when it's signal, so what is there? So you have a signal in, so this is a block, and then say for example a device. Then this one is maybe a network called tuning network or matching network. So this network, if the signal is not matched, then what will happen? Signal will reflect back. It will not go to the device for amplification. Suppose this is your amplifier. So you require some sort of matching in the system. What does it matching network will ensure? That the signal A sin say omega t, that signal will pass through that matching network, and this will actually come to the amplifier for amplifications, because the signal which has being, say, it is a voltage source Vs. Now a voltage source should have a series resistance Rs, but it might have a complex impedance. Say I am assuming to be Rs. Now yourself you say that this is Rs, so what should be my impedance of my device? Suppose this block is not there. So what will be that impedance? Should be Rs equal to RL, as you know from your analog basic electronics. But is it so? Because you yourself tell that the Rs is not pure Rs, or the devices are not resistive, they have a capacitive and inductive part also. So you need to have a matching circuit which will ensure that the effective impedance as seen from this end and as seen from this end would be the same. So your device should see it is a 50 ohm impedance, and your source should also see that it is also a 50 ohm impedance. Then and then the maximum power gets transferred. Otherwise, whatever be your tower signal, if you look from your cell phone, catching the signals by the antenna, it will not go to your LNA, the amplifier. You need a tuning circuits as well as you need a matching circuits. I spelled about the tuning circuits. Why do you mean by the tuning circuits? Because if you look at the signal spectrum band, I will come into that. N number of signals are actually pervading in the atmosphere. You have to detect the correct signals. So this network should also have a tunable capacity, that it should particularly tune to 915 megahertz, as well as whatever power is getting in the systems, that should be through to my amplifier side. So you need a matching. That is not applicable in case of analog design. This is the complexity or challenges for RF design. And this is also true for the load side. Load side is not only simple RF, you will also need a matching network. What is that load side? It can be a mixer, it can be another antenna for transmitter. And an antenna means what? 50 ohm, always we check, or BNC cable we know as 50 ohm. But your devices are not 50 ohm. So you have to do some matching or impedance transformations, so that from both the side you will have 50 ohm impedance, or you will have the terminal impedance, so that maximum power gets transferred. Am I clear? So this is the matching network we require. Next is the sensitivity, because I have already explained the noise. In case of high frequency, the noise is another complex. What is the noise in case analog design? Primarily we know the thermal noise, right? 4kT delta F. Okay, this is the thermal noise, electron being moving around your conductor randomly, and that creates the thermal noise, and that is proportional to the temperature and proportional to the bandwidth, that is 4kT delta F. But along with that thermal noise, in case of RF, there are several other noises. 1/F noise, shot noise. There are 3-4 types of categories of noise that will also affect your design. So you have to be careful about those noises too. Then sensitivity. Sensitivity is quite important. In some cases you say that my Nokia phone is not so sensitive or very good sensitive compared to the other brand. What do you say? Because the front end, if it is not sensitive enough, you may not be able to detect the signal even if you are on top of your signal strength. Your detection sensitivity is very, very important. And what is the sensitivity? What is the minimum level it can detect? And what is the minimum level? Is just above the noise. If you look at the noise as the platform, which is my reference frame, any signal beyond that should be detected. So that detectable limits is the sensitivity. Then another term is called the dynamic range. Dynamic range means what is the maximum signal you can detect, ensuring the linearity of the system. Suppose signal strength is very high and reaches to its nonlinear region, then what will happen? Suppose this device reaches to the nonlinear region, what will happen? In spite of frequency omega, you will get all other harmonics, because any nonlinear device, when a signal is passed through, then it generates other frequency too. So that is simply a wastage of power, and they will intermodulate, and they will create a lot of sparse noise interference to your actual signals. So Dynamic range is the range at which you are ensured with the linear operations of your device. And what is the minimum signal? It is the minimum detectable signals which can be detected by the systems which is beyond the noise level. So total range is the minimum signal detection and the maximum signal detection is the dynamic range. So difference of that is the dynamic range. So all your GSM mobile phone or CDMA, whatever you have, these are the major things. What is the sensitivity of that? You know, what is the sensitivity of your GSM phone? All you have cell phone is roughly minus 90 dBm. Okay, so the kind of, for example, a Bluetooth, it is even less, say minus 123 dBm. So these are the different ranges of sensitivity you want to have. And more the detection means if you want to really detect the smallest possible signals, then the cost of your sensors, cost of your receiver front end is becoming high and high, because you need a very powerful or highly sensitive LNA. I will talk about the LNA in my next after a few slides. So now let us go back to a little bit of history, that what are the various ways people have tried and for RFIC implementations. There are few commercial aspects to that. One is the development cost. In case of MMIC means where the discrete components are used and they are actually being implemented. On your cell phone, if you just break any cell phone, you will find small components are actually on a PCB. So there are multi-chip solution. Mainly there is a baseband processor, a power amplifier, the RF front end and a signal processing. So all 4, 5, 6 major ICs are actually on a board, and you will find with the antenna if you look at the cell phone. Now people are trying whether it is possible to implement such devices on a single chip solutions. So the cost will be pretty less. Maybe the cost of its development will be high, but once it is developed, then it is a batch processing. So I can reduce my cost like anything. So I can make $20 or $10 for a whole cell phone. So that's why we call it the bill of materials. BOM cost is low, and it is depending on, for RFIC, it depends upon the volume and die size. For example, I want to design a complete transceivers where the die size is 2 millimeter into 2 millimeter. Mind it, 2 millimeter into 2 millimeter is the die size, and you have to have the complete transceivers so that I can integrate on my watch and have a cell phone and have a mobile TV, and I can have a WLAN and Bluetooth too. So that is not becoming a story. People are working on it. We are also working in the same area. It's called divergence of various technology. We are keeping the area and the cost less and less possible. So that is also another very, very interesting approach for RFIC. That is how to converge the different technology in the same platform. So these are vis-a-vis, there are various advantage and disadvantage compared to that, but primarily it is the smallest, it is the lightest, it has got huge flexibility, and it has got a huge potential of reducing the cost, like bill of materials, and finally integration with the other devices. That's why the single chip solution and RFIC design is becoming a very hot topic in nowadays. Now, very quickly I say that, especially for you people, because you should know about what kind of background you need for RFIC design. You know that there are many digital designers. There are also analog designers, but not many as digital designers. But analog design or digital designs, this is something is very conventional. But in case of RF design, it is really you need the designer's concepts. That's why very few actually RF designers are there throughout the world, because they still believe some black magic. I don't believe in black magic, but it needs experience, expertise, and sense of various branches of communication, physics, and engineering. So I just put it in that way, that what you need actually, if you want to be a good RF designer, what faculties you need to be improved. Communication theory, you really need to know what kind of modulation scheme, what kind of protocol, what is the system bandwidth, all these things are required. Then you need to know about good amount of statistical, like random signals analysis and all, because the noises and all this. Then transceiver architecture, what kind of architectures finally will be through. Then CAD tool, that is actually for RF design there is no such CAD tool exist. In digital design, millions of chip or billions of MOS devices can be integrated because you have a very tested CAD tool. But in case of RF design, no such CAD tool exists. Believe me or not, just to integrate 3 or 4 transistors to design an LNA along with their passive components, it requires around 3 to 6 months for a designer. It is really challenging. But once you have that expertise, then you are the king. Then you know what are the tidbits of doing an LNA which can be used for cell phone, or it can be used for missile tracking, for ICBM, or for satellite applications. Then you will be an LNA expert. Or for designing a power amplifier. So there is hardly 1 or 2 transistors, but it takes months after months to tune it up to get the actual efficiency and the linearity of the systems. You should be aware of the wireless standards, that is whether it is IEEE 802.11a or B, or IEEE 802.11 15.4 for Zigbee or Bluetooth. Also you should be aware of the standard. For example, now people are talking about Vibri. Nobody knows that till, because it's not flashed that way, but people are talking about communication inside the body, inside the human body. That is another RF application is coming up. How to make different probes in the body and how they will propagate, because the probes are now with the, all the probes are now with the wires. Now people are trying to make it without wire. So the ECG, EEG, all this kind of sensor based signals can be detected as well as transmitted wirelessly. And some of the signals will also passes through the body and some to the air. So you need to know about what kind of correct protocol for biomedical applications will be used for wireless transmission. Huge amount of research interest is coming up in this area, and the special protocol will come up by like Zigbee. Zigbee is already come up, like nearly 200 companies have accepted that proposal for sensor application. We call it MOTS, or smart sensor or sensor networking. You can have standalone sensors that can receive the signals and transmit it, and they can use as a sensor node as well as a cluster. They form a clusters for a redundant network for any sensing system. So you know that it's a huge domain, means where you have the options for learning different faculties of engineering and the science. And above all and top of all is the physics is pretty important. Why physics is becoming so important? Because now people are not talking about 0.18 micron technology. People are talking about 45 nanometer technology, or in future when you will be graduated, you will talk about 10 nanometer technology. Maybe at that time high frequency and that range, the physics is quite complicated. What will be the transport of this semiconductor at that region and how to interpret from that. And the second one is the famous octagon. You know that in analog design or in RF design, there are few performance metrics. Those performance metrics are, for example, noise, linearity, gain, power consumption, supply voltage, speed, input output impedance, all are called the performance metrics. But those performance parameters, they are not independent to each other. They are highly related to each other. If you want to increase the gain of a system, that your power consumption will go up or your linearity will be affected. So you cannot actually just monotonically you want to increase or decrease, that won't happen. It's a multi-valued system. That means if you look at the computational approach, you need some sort of evolutionary computing approach. For example, genetic algorithm, or for example particle swarm based optimizations. In order to have the optimum design because it is a multi-objective function. I want to have the maximum gain, I want to have the maximum linearity, I want to have the minimum noise, and I want to have the minimum power consumptions, and they are all diagonally opposite. So you cannot have a global an unique solution to that, right? So you have to have a global solution. You have to find out the global best. Then the global best should be obtained by some heuristic or by some evolutionary approach. Here lies the huge scope of computational people, because all the time you cannot have a closed form equations of those objective function. For example, with a complex circuit, if you want to have exact differential equations of the gain or the closed form equations, it will be easier, but sometimes, for example, power amplifier, which is a nonlinear device, or for an oscillators, you cannot. So you should have some mathematical tool to support your optimization techniques, and where huge scopes are there. And finally, to have a computer aided or automated design of, say, LNA or power amplifier is the final goal. That suppose I have given with a set of metrics, for example, the gain, the power consumptions, the linearity, then I will have some sort of framework, a CAD framework, and I will explore that what topology will be the best for that. The first cut design is to find out what topology should be the best. Once these people, the CAD people, or those are good in computation, they quickly find out this is the topology which can give you the best performance. And you can also say some of the topology can be discarded because they will not provide you that specs which you want. Very quickly, if you can get that information, you reduce your design cycle. What is the design cycle? Typically, a design cycle is 9 to 12 months. Now, if you make an expert system, then it can be reduced to 3 months even. Then once you have zeroed down your topology, then next part is the fine tuning. And fine tuning required that expertise. And finally, if that expertise can also be, make a platform for an expert system, then you can actually have an expert CAD tool for designing an RF system. So that is the, I should say, the challenges those who are inclined to the computational approach, they want to go into that subjects. One is the device area, other one is the circuit areas, and the third one is the computational, huge complex mathematical tool you require, and we reach really some heuristic search, or really you require some particle swarm optimization, so kind of evolutionary algorithm technique. So these are the various circuits and system, the design issues. I am not going into that, but whatever I have essentially said, this is summarizing that one. That what are the, for example, the phase shift of the signal is significant over the extent of component because its size is comparable to the wavelength. That is the whole reason why the lump parameter model fits. When the component size is comparable to the wavelength, then if the component size is this and the wavelength is this, then what is happening? You will find ups and downs. The components are filling the ups and downs of the signal, so that phase is changing. Whereas if the wavelength is this and your component size is this, then you can always approximate the signal phase is constant along the, so there is no, so lump parameter model will valid. That is why lump parameter and the distributed parameter models. So these are few points. For example, circuit losses cause a degradation of Q, a reduction of frequency selectivity and noise performance. Q is another very interesting measure. Q means quality factor. What is the power dissipated and what is the power given in the systems? Q value, if Q is high, means always it is better if Q is high. That means your power consumption is less. So if you have a good matching network and tuned, sharply tuned, for example, suppose this is one tuning network and this is another tuning network and that is another tuning network, and finally it is becoming very sharp. So which Q is high? If you look at this way, then Q is increasing in this way. That is, for sharp tuning, you want to have, say, FM band, then 107.3 and another one is just jumping close by 107. Then you need a huge tuning circuit. The Q should be pretty high to select that signals and isolate that one so that your FM signals would not interfere each other's. For example, reflection issues, I have also mentioned that reflection issues is quite important. When the impedance are not matched from the source to the load, then the signal will reflect back to the source. What will happen to the source? The source will be heated up and it will be damaged. So, and if its antenna is matched with your LNA, that will happen. All your signal will go to the antenna sides, and so you need maximum power should be transferred to the load, and that is quite important. Then, if you look at the number 8 is a nonlinearity, which causes distortion and unwanted frequency components. Even for RF application, you are knowingly or unknowingly using the nonlinear property of the devices. In which cases? For example, in case of an oscillator is a perfect example of a nonlinear operations of a device. It's not a linear circuit, it's a nonlinear operations. You can generate many frequency out of an oscillators. Then you have to use a tuned circuit. So every oscillator you need a tuner, right, to select the desirable frequency, but you are actually using the nonlinear part of the device operations. Whereas in case of mixer, what is the mixer? Mixer is nothing but is a product of two signals, say A sin omega t into B sin omega t or B cos omega t. Then if you multiply, what is the circuits is known as? Is called the mixer. This mixing means multiplying the two signals. And finally, what is the output? Output is the difference of these two signals, omega 1 minus omega 2 or omega t minus omega 1 at the first order approximations. So you are using the nonlinear property for making some circuits, namely the mixer as well as the oscillators. So this is more or less the first part of my lectures, which tells you the very basics of the RFIC design. Now I quickly go into the various issues like noises. For example, a resistance. If you can model the resistance, what is the noise of a resistance? Now 4 kT delta F, and this 4 kT delta F is the noise either in terms of voltage in series with the resistance or in terms of current, which is 4 kT delta F by R, which is in parallel to the resistance. So you can look carefully that a noise contributed by a conductor or by a resistor R can be a voltage source in a series whose value is 4 kT delta F, or a current which is parallel to the resistance, which is 4 kT delta F by R. So immediately you find that if you increase the resistance or if you increase the temperature, then your noise contribution, the thermal noise contributions will go up. Now it is not only the components, the resistance components, but also the MOS devices. If you know the MOS devices, they have a channel. Okay, this channel is, if you look at the MOS devices, I am just going into that. Suppose that if it is the channel is here, then what will happen? This is the source, this is the drain, and this is the gate. So if this channel is here, then you know that when you apply a voltage with respect to source, a VDS is supplied to that plus VDD, and its source is grounded. So what will happen? And gate is, say, with a voltage source VG, the channel is formed. Then it is actually acting as a resistor, as a channel resistance. So same noise it will be created in the channel, and then same formula can be used, the 4 kT R delta F, where R stand for the resistance of the channel, the MOS devices, and we can use it that one. Then you can use the MOSFET transistor noise, the channel noise, because of saturation, because of the thermal noise, is 4 kT gamma GM, where gamma is the parameter when VDS equal to 0, when gamma equal to 1. And for long channel device, what is do my long channel device? When the dimension is 2 micron, 3 micron or 1 micron, but when it is less than 1 micron, then what happens? That it is no longer is a long channel, it's a short channel device. Then gamma values are actually goes into 2 or 3, it increases more, and for long channel device in saturation is 2 by 3. So these are the noise model of a MOS transistor channel. So what we have found that a MOS transistors, suppose you have a resistance and then you have a MOS devices and you have a channel here. So that resistance will contribute to the noise, which is 4 kTr delta F, and also this MOS channel resistance will also contribute a noise which is equal to the 4 kT gamma Gm. What is Gm? Gm is the transconductance. What is the transconductance? It is called del ID by del VGS, where VDS is equal to constant. For a given VDS, del ID del VGS is your Gm. So Gm 4 kT gamma Gm is the noise equivalent or the thermal noise of the transistors, and gamma value depends whether it is short channel or long channel, or whether it is in saturation or it is not. Then there is another one, is called the gate induced noise. What is the gate induced noise? I am working with high frequency, so there is always a charging. So what is happening? Suppose the gate, there is some AC signal on top of that, some noises incorporated in the system. Then what is that gate? Gate is basically metal oxide semiconductor, or metal may be replaced with the polysilicon. Now it is essentially a capacitor. One is the oxide cap, another one is the channel cap. So basically it's two capacitors in series, right? So if there is a charge across that, and if there is a time perturbations like a noise, then what will happen? The charge will be modulated. If charge gets modulated across the capacitor, what will happen? dq dt means there is a current. So that current will be introduced in the channel. So that is known as the gate induced noise, and that is explained as, if you look at its corresponding voltage source, is equal to 4 kT delta Rg into delta Rf. And this is the noise model. The gate induced noise model is the corresponding V square Ng is the noise of the, what is that? The noise contributed by the channel plus the equivalent noise created by the resistance. Because suppose there is a gate induced noise, we know, because of the high frequency operation, but how to put it in your cadence platform, in your simulation platform? What you will do it, you just think of that what noise can be created if there is a series resistance added to my MOS devices at the gate. Then equivalent thermal noise, if it is equal to my gate induced noise, then I can place the series resistance with the gate, and that can serve my purpose. In spite of going details into that modeling part incorporated in your simulation tool, you can very well make a small signal analysis by incorporating a resistance in series to that. Now that is the tricks, you can always use that one. Next is the short noise. A short noise, you should know that whenever any charge is crossing any junction, for example a PN junction, you know PN junctions, when it is doped with a p-type dopants and is n-type dopants, you form a junctions, and when some current, any DC current is passing through that, then what will happen? There will be charge trapping and detrapping, and that causes the short noise, and that is equivalent noise, means the current equivalent noise is equal to 2q IDC into delta F. So what do you understand from that? If you even forget everything, what do you understand? The noise sources either from thermal noise sources from the gate induced noise sources from the short noise, they can have an equivalent representation either in the voltage connected in series with the load, or a current source parallel to the load. So finally I have to find out whether is the current equivalent or voltage equivalent of the noise, and I have to understand the physical model for representing that the noise. That is why the physics part is important. For example, the flicker noise. The most important part is the flicker noise, because if you look at the flicker noise, it originates from the, if you look at the MOS devices, what is that? You know that this is my silicon, and on the top I am just giving a MOS cap. These are oxide and you have the metal one. So if it is SiO2 or Si3N point, it is a metal. the oxides are not defect free. They have defects basically. They have some trap centers. And trap centers are sometimes very close to the semiconductor and oxide interface in this say 10 angstrom or say 100 angstrom above the interface. And that's what happened. The challenge is full of charge, the mobile charges. They get attracted to those traps, and they are constantly trapping and detrapping in those oxide trapped. They actually constitutes the 1 by f noise. You can understand physically that if the frequency is high, then what will happen? The charges are modulated at high frequency. They are pretty fast modulating. The trap centers, they have certain escape to attempt frequency, because trap centers, they will trap it and detrap it. They need some time, right? Response time. If the frequency is operation is much higher than the response time, then my trap centers are less affected. Exactly, it is reflected here. That is the IN square, which is representing the flicker noise, is inversely proportional to f. That means if f increases, then the flicker noise goes down. That is like some sort of relation you will find that it is like that. So actually it is now going to the ground level. We call it the ambient noise level, minus 174 dBm. I will explain at normal temperature at say 270, that is 300 Kelvin. So you understand how the physical process, the physics model, as well as the device and the mechanism at high frequency is finally governing my noise incorporations. In analog, you have only know that thermal noise, 4 kTr delta f. You are happy with that. But in RF, again I repeat, not only thermal noise, there will be gate inlet noise, there will be short noise, there will be flicker noise, and there will be other noises too, which is second order function of frequency, that is 1 by f square, 1 by f cube noise. But for time, for this time I am just concentrating on 1 by f noise. So that's the noise part. Now I coming to the next part is a noise figure. Noise figure means you need to define some parameters, right? That what is the noise parameter of a system. You cannot think that noise of a system is 0 or a source which is noise free. Ideally everything is noise free, but actually come to the ground and design something, because we are all engineers, right? So we cannot think in the ideal platform. I have to look into my noise issues too first. What is the contributed by the source? What is the contributed by my design block? I have to be careful. So therefore, we define a factor called noise factor, which is the total output noise power divided by output noise due to input source. Because input is providing some noise and output is what is the maximum output power, noise power. If you divide that, you will get the noise factor. And if you take the logarithm 10 log of this noise factor, you come to a figure. It's called the noise figure. That means if a system there is no noise, then we call the noise factor. If the system is no noise, that means noise factor becoming 0, and that means it becomes noise figure becomes 1. But in practice it is not possible. That is, noise figure of a system is 1. It is the ideal case. Noise figure of a system is always greater than 1. For example, the best LNA you can design may be less than 2, but you cannot think of 1, right? So noise figure is always greater than 1, because there is noise in the source as well as noise in the system which you are designing. Now this one is another important slide. I will very quickly go through it. That what do you think about the noise? That I want to reduce the noise, as simple as that. Everybody will say that I want to reduce my noise, and I also wanted to have my input signal maximum input signal get transferred to my system. Suppose this is the black box. This is my signal going in, and then I want that noise figure should be as low as possible, and the maximum signal get transferred to the system. Okay, that is essential. Everybody wants that. my battery life will be less, everything will be pretty high. I will see a very clear signals for my cell phone. But unfortunately, you will find that two conditions, that is one for maximum power transfer and other for minimum noise figure, they don't converge. If you look at here, the maximum noise figure, what is expression for these circuits when RS is the source and RP is the load, then you find that when noise figure is, say, I want minimum noise figure. What is the minimum noise figure? Is 1. So the RP should be infinite. This one should be infinite. Clear? As high as possible, then I can neglect that term. But if you increase the RP, then what will happen? What is the condition of maximum power transfer? The source resistance should be equal to the load resistance. So RS should be RP. So yourself can conclude that my maximum power transfer condition and the minimum noise factor or noise figure condition, they are not same. So you have to make some sort of optimization, and that is the optimized resistance for these circuits. So you understand what is the meaning of optimizations. When two parameters, they are not converging to a minimum or maximum value, we have to optimize that one. And so you need a lot of mathematical tricks to do that. So that is one examples of doing optimizations of that. Next one, for example, an receiver, I will come into the receiver side. Suppose any RF block cannot be a single unit. There may be stage 1, stage 2, stage 3, stage 4. And each one have a gain or attenuation and a noise figure. Then if they are cascaded, then what will be the overall noise figure of the system? For example, my GSM phone, this cell phone, the kind of noise figure I want is 6 to 7 dB, because the dynamic range is around, what is the minimum signal strength it should be able to detect, is minus or 89 dBm or 90 dBm, and it is the dynamic range is around 47 dBm. So overall noise figure is 6 dBm or 7 dBm, and it has got various components called functional module in the systems. But overall, because my antenna and then the output in between the whole RF block, so I have to estimate that noise, I have to estimate that gain to find out what will be my overall gain and overall things. What we find that noise figures, for example, we start with two stage 1 and stage 2, having a noise figure NF1 and gain G1, and other one is a noise figure 2 and gain 2. They are cascaded. If you find that the total overall noise figure is the noise figure of the first stage plus the noise figure of the second stage minus 1 divided by the gain of the previous stage. That is the important part to remember. That is, the contribution of the noise of the first stage is coming straight forward to the system noise figure, but the contribution of the second one gets reduced and then actually scaled down by the gain of the previous section. So the first module of the RF front end is the most important one. The noise figure of the first block, the stage 1, there is no scaling down by the gain of the previous stage. That is, after the antenna and the matching network, the next stage should have a very, very low noise figure and a very high gain, because we immediately find out the A1 is the gain of the first stage, and that is reducing the noise of the second stage, the contribution of the second stage. So my first stage should have high gain and low noise figure. Clear? That is comes from my mathematical model. And what is that component, or what is that functional modules? Is called after the antenna. If you look at the antenna, then this is the matching network or band pass filter, because I want to detect my desirable signals. What you do it here, 915 to 975, 950 megahertz center bandwidth, etc., etc. Then next block is called low noise amplifier. First block, that is, it has got a huge gain of how many? 16 dB roughly. I am giving a typical figure. And what should be the noise figure of the systems? Less than 2 dB. because there is no calibrating factors to reduce the contribution of the first stage, that is the stage 1. Next block after the LNA is my mixer. I will explain that mixer, that will actually, because your signal is coming at frequency say 2.45 gigahertz. For my Bluetooth, for example, I am detecting signal from laptop. Okay, that is the 2.4, same circuit there in the Bluetooth applications. This is a matching network and then the low noise amplifier. And the frequency of the Bluetooth is 2.45 gigahertz, whatever you are using here. So next block is the mixer. What is that mixer? The mixer is basically converting the frequency from 2.45 gigahertz to the lower frequency, depending upon what kind of topology you are selecting. If it is a direct conversion receiver, you can convert it directly to the baseband. What is the baseband? 25 megahertz, 100 megahertz, 70 megahertz, 1 megahertz, depending upon the kind of applications you are using. But if you have number of stages called super heterodyne or heterodyne receiver, then what is happening? This kind of mixer, they actually lower the frequency, down converted to a intermediate frequency, then again goes to another intermediate frequency and gradually to the baseband. So different IF stages they make it. We call IF, intermediate frequency stages. So number of blocks would be more money, more cost, more silicon, therefore not a good options for on-chip, single-chip implementations. Normally nowadays people are trying for single-chip solutions, some kind of homodyne or direct conversion receivers, where the mixer will directly convert the signals from 2.45 gigahertz to 1 megahertz bandwidth, so that I have my baseband straightforward, because my baseband is of that bandwidth. Now consequently, if you have n number of stages, then if you look at this equation, the noise factor is contributed by NF2 minus 1, the gain of the previous stage, then the mth stage, it is NFM minus 1, then the product of the gain of the previous stages, that is from A1 to AM minus 1. So you can always find that the mixer, it may not have a gain, it might have a 3 dB attenuation, and it may not have a noise figure of 2 dB but 8 dB. But what is the advantage of that? You immediately find out that this gain, the gain of this LNA is scaling down the mixer contributions very easily, so that actual noise contributed by the mixer will be much less compared to the LNA, because there is no such stages below or before the LNA. So these are how an LNA and the filter can be used, and we find that the noise figure of the LNA plus the filter loss is the overall noise figure of the systems. So this is classic examples of how to calculate the noise figure of a say the common source amplifier. So you have to calculate the noise contributed by the resistance, by the channels, and then add on this and finally get the compressions of noise figure equal to 1 gamma GD0 plus G square MRS, etc. So these are the values you can calculate, because you have to go for the small signal models. Then whatever we have taught my earlier few slides, you can get into the total contributions of the noise of the systems. That is for a simple and a common source single stage amplifier. But look at the system. When you have a cascaded stage or folded structure, the kind of complexity in understanding the overall noise will be much more complex. So this is the linearity of the system, and if you look at the linearity, what in nutshell we understand the linearity? Suppose a system has gone to a nonlinear device, then what will happen? The output is not only a function of xt, is a linear function, there is also the x square and x cube terms too, right? There are cubic terms, square root square terms, and so on. But what is the meaning of that? Suppose this is my nonlinear device and this my signal which is say xt. But if the yt, that is output, is not only a function of xt, but also it is a function of say k1 xt whole square plus k2 xt whole cube, then what is happening? These are all say sin omega t or cos omega t. So this cos square or omega or sin square term, they will contribute to the harmonics of that. If you can make sin square omega t, what does it mean? Cos to omega t, that way you can expand this one. And you can also expand this term with intermodulations to that, I will show in later on. So that is the reason why you will find the harmonic contents for a nonlinear devices, because they have the other, apart from the first order approximation, the linear term, you have the other quadrature and other cubic terms too. And if you square or cube that one, and then you find that harmonic contents. Now what does it mean, that harmonic contents? If you look at the power conservation, whatever power is fed to my system is through my signal, right, and the DC biasing. I am not giving any extra power. So suppose, what is the significance of that plot? This is my input signal, amplitude for example. This is the 20 log n, so it is a power, okay, and this is the output. I am plotting it. If it is a linear system, what would happen? It will, at 0 it is 0, they wish to go linearly. But what happens? It drops. Why? Because after that signal, you cannot neglect those terms. After a becomes, when a is very, very small, then you can neglect those a square and a cube terms. But when you cannot neglect those terms, what will happen? This will create those kind of omega t, 2 omega t, 3 omega t, 4 omega t, 5 omega t, those terms will come. But your power is constant, then what will happen? Those energy will be distributed to those harmonics too. This is the output at the fundamental frequency omega t. But output energy or power is shared to all other harmonics. So definitely you understand the output power will be reduced at the fundamentals. So that's why it gets reduced. Now if you quantify that, how much power gets reduced? Say I say 1 dB power compression. Then 1 dB power compression is the measure of linearity. So that is the input power at fundamental frequency, for which the output is reduced, power is reduced by 1 dB. That is known as the 1 dB compression point. So that is the measure of the linearity of the systems. So we understand noise contribution, we understand linearity, we understand little bit of gain, and we understand the noise factors and noise figures. Now another, very quickly I am saying that signals that are going, that are not only a single tone, that is not only a sin omega t, xt may not be a sin omega t, xt may be combination of another one, a sin omega 2t, maybe multi-tone. Then what will happen? Then my complexity for a nonlinear devices will be much more difficult to understand. You find that they not only produces the harmonics, but their intermodulation products, that is omega 1 minus omega 2, omega 1 plus minus 2 omega 2, 3 omega 2, like this. They are called the intermodulation term. Now if those intermodulation terms somehow gets converts to your desirable IF band, then what will happen? You won't get your signals. Because what is the role of a mixer? Role of a mixer is to down convert your input signal to the baseband or to the IF band, depending upon the kind of structure. Now if the intermodulation product, the mixer is a nonlinear device, they convert to your desirable region, like here, you see here, this is my desirable output. Now one of the intermodulation products is converging on that, and that intermodulation is even bigger amplitude than my desirable output. What will happen? You won't see listen my voice, you will see noise. So that's why the intermodulations are very complex and very important for nonlinear devices, and that needs to be understood. Not only understood, we have to make necessary circuits how to eliminate the nonlinear the intermodulations and how to increase the linearity of a system. For example, suppose I am designing a cell phone, I am designing a base station. For cell phone, linearity requirement is say -10 dBm, but in case of baseband, where the signal strength is much higher, the base station, because they are actually the center. Cell phone is receiving very small signal, -80, -90 dBm to -47 dBm, very small, but whereas baseband is pretty high. So think of it, if the signal goes to a baseband front end, and if it goes to the linear region, nonlinear region, then it will create a lot of problems. So linearity of base station front end should be pretty high, say 10 dBm, not -10 dBm. So that is called the design of front end for linearity improvement is a major challenge, not reducing the power or not increasing the power, but even using the same other parameters like the noise figure, power consumption, keeping intact. If you can increase the linearity, that is the challenges in RF design. So now I am going into some of the basic things of devices, that high frequency, how do you look into these pictures? For example, a silicon technology, which is basically the bipolar, the BJT. Bipolar means both electrons and holes are the carriers, and MOS devices is a single pole devices, either electrons or holes are the major transport element. And then you have the bipolar has got two classifications called junction isolated BJT and dielectric isolated, depending upon the fabrication steps. And MOS devices are PMOS or NMOS. And then you know that MOS devices also having both the PMOS and NPOS, that is called complementary MOS devices. So our cup of tea is that CMOS. So we will actually make the CMOS as our main component for making the RF circuits. Why? Because if you look at the power delay product, the CMOS as the lower one, it has got the minimum power consumptions and delay is less, but for ECL delay is pretty less, very fast. But if you look at the power delay product, then compared to ECL or TTL, the CMOS is the best one. So our choosing, we are choosing for low power application CMOS. So now for high frequency applications, there are another, you can, for example, I want to make few gigahertz oscillator, then sometime I want to increase the GM value, that is transconductance value. Transistors will provide to BJT some higher values of GM compared to the MOS devices for a limited size, because you know that GM of a transistor is IC by VT. So by changing the transistor current, you can increase the GM, whereas in case of MOS devices, the GM is equal to root over of twice ID mu n Cox W by L. So you want to increase the GM, you have to increase W or reduce L. But if you want to increase W, then what will happen? Your capacitance will go up, the parasitic capacitance will go up. So your cutoff frequency will suffer. Therefore, it is not always possible to increase the GM or transconductance of a MOS device so easily. Therefore, BJT sometimes used to get higher GM, okay, but power consumption is pretty high. It's higher than the CMOS. That's true. Now come to the pros and cons of CMOS and the BJT. But even if you look all the pros and cons, you find that basically the cost, area, and flexibility of the design, and with the recent technology, initially people could not think of having a 20 gigahertz FT, that is cutoff frequency for MOS devices. But now we are going to 100 to 150 gigahertz. So cutoff frequency 150, so you can have an operating frequency of 10 gigahertz, 20 gigahertz oscillators. So now you see the market now. So the whole domain is CMOS, whereas the TTL and other devices are not much having the same markets. But CMOS, is a major chunk of market in the CMOS. That's why we are choosing CMOS based low power RFIC design, because it is quite cost effective solutions and on chip integration possible, because you want an on chip integration, you want the miniaturized circuits, you want low power consumption, and that is at low cost, and you want multi-functionality. Nobody now wants a single for example a mobile phone only for voice communication. They want to transmit data, WLAN 5.6 or 6.3. They want to have Bluetooth, so 2.4 gigahertz. They want to have the video online streaming, DVB-H, or terrestrial streaming. You know that all over world people are coming up with portable TV on your cell phone. So it requires 470 megahertz to 620 megahertz. So all this application, protocol, complexity. So CMOS can give you to that diverse, that can actually give you optimum solutions in terms of cost and area, the CMOS. That's why CMOS is so much popular. Now going to the sample stage, that how this substrates, what are the basic stages of CMOS. You start essentially with a substrate, either maybe P or N type. What is the dimension of that? Normally we use 4-inch, 8-inch, 16-inch wafer or 12-inch wafer. Wafer mean is a circular disc, and the thickness is 270 micron, 640 micron, 570 micron, or even 200 micron. So depending upon this thickness is the substrate. Clear? On the top you have the active layer. What is that active layer? You have an AP layer, monolith. That means you actually grow an AP layer by ion implantation or by some epitaxial technique on the top of silicon. So substrate is mere holder, but this AP layer is my active layer on which the devices are being fed. Now you have the filled oxide, okay, on the top of that. On the top you have the oxide layer. You know that, so immediately you can recognize the filled oxide is serving as the barrier layer or isolation layer from the other devices, whereas this layer is pretty thin. How thin? For example, 0.25 micron technology, the thickness of the oxide layer is 50 angstrom, whereas the oxide, if you look at the filled oxide for isolation layer, it is 2000 angstrom, 2000 micron. So it's pretty big, pretty thick. On the top you have the polysilicon. Polysilicon is almost like a metal. It is polycrystalline silicon. Conductivity is pretty high. Okay, so that is the polysilicon growth, not metal, but polysilicon used because it's the same silicon process grown by either sputtering or PCBT. Then you grow the source and the gate and the drain, and this is your gate layer. So you have the N plus, because this is the P layer. On that you have to grow what? N channel, right? So you have the N plus source and N plus drain. Okay, and then you have the vias or contact for source and the drain. Then you have the metal 1 and metal 2, the contacts, and on the top you have a thick oxide, that is for the passivation, that you encapsulate all your device on top of that. So whole thing, you have the source, you have the drain, you have the gate and corresponding contacts through metal 1 and metal 2, that is called the vias. So that is a single devices for a silicon, either maybe P type or N type. Okay, and depending upon what kind of substrate, suppose it is an N type, right? Now if you want to make a P type, then you take N type substrate, then you make NAP layer, then you make the complementary, the P++, and you form your P type MOS. And when both exist in the same die is known as a CMOS or complementary MOS devices, where you can use both the CMOS, both the NMOS and the PMOS operations. You can use and reuse the current for minimizing your power consumptions. You know that CMOS devices, what is the advantage? That is, when they are in series in CMOS devices, okay, then this is PMOS, this is NMOS. Then what will happen? That when this transistor is on, then this is off, and when this transistor is on, then this is off. So if you look at the VDD and if you look at the ground, then the VDD is never seeing the ground, always it is cut off by this one. So there is no essential current flow to the ground, so power consumption is very less. Only when the crossover time, when both the transistors are on, then there will be a current pulse. So if you look at the power consumption, it is almost like that. So this is the current pulse, very small duration current passes to the ground, therefore, and this is the leakage current. So you can think very well the CMOS is the most power efficient logic gates for implementing that one. And this is the metal 2 for the final contact, and then this way it contacts, and then another CVD for, and finally how it looks like your VLSI. So you find that in our CMOS 0.18 micron process, your epi layer is here, the devices, MOS devices are here, the N well, P well, the gate and the poly layer. On the top you have 6 metal layers, okay, and these 6 metal layers are basically for your interconnects, for making routing around those devices, millions of components to be connected through those running wires, and they have to be connected through VS, and these are the vertical lines are called the VS. And the top metal layer is made exclusively for fabricating the inductor and the capacitor, because it is little bit thicker, so that its resistance is less. You know, the thicker conductor offers less resistance, and therefore it is used as the passive component layer for making inductor, etc. For example, one inductor you have seen that how it has been fabricated. So this is now, if you look at that 6 metal 1 poly 1 AP layer process, 0.18 micron standard CMOS process, then how this simple inductor or simple connectors becoming complex. If you look at here, these two connectors, right, they are in different levels and they are separated by an oxide layer, right. Now if there is a signal passing through them, both of these conductors, what will happen? At high frequency there will be mutual coupling, and that is so you can effectively model that two running wires separated between the oxide layer by a capacitor and by a mutual coupling. Okay. For example, if you look at this, look at those vias. Vias are what? From metal 1 to metal 2, level 1 to level 2, they are connecting. But those vias can be modeled, as I say, when the frequency is high, wavelength is comparable to the size of this, you cannot take the lump parameter model, you have to take the parasitic. So that is inductor and the resistance. So a simple vias are not simple resistance, but they are having an inductor too. For example, in case of channel, the resistance, the N plus well or P plus well, they have certain resistance which is replaced with R. Then the polysilicon, they have a sheet resistance, so that resistance will come. Then the silicon, which is the AP layer, had from the substrate, the capacitance, and also the resistance. You have a eddy current loss in the systems, and also the gate to source capacitance, gate to drain capacitance, source to bulk capacitance. All those capacitance are coming into the picture to make your design more and more complicated and more challenging. That's why the last line, the Maxwell EM equation is required, and which is a challenging issue when you are working at high frequency. For your analog design, you don't bother about that. You are talking R as R, C is C, L is L, and that's all. So this is the standard MOS model. If you start from your gate, then what you find? That gate there is an inductor Lg, then resistance Rg, then as GM-pi model you find there is a CGB, that is gate to bulk capacitance, then there is a gate to source capacitance, as well as the resistance, the input resistance R1 and the source resistance and the source inductor, then the corresponding current source GM into VGS. VGS is the voltage across the capacitance CGS, then the drain to source resistance in parallel to that current source, and then there will be C drain to bulk, and then there will be drain resistance and the inductor, because each resistances are in the transmission line model is actually they have inductor and the resistances. So finally, when you actually go for a simple MOS model, in case of high frequency, you have to take care of all those capacitances in the netlist. And if you look at the MOSFET, these are very interesting two figures. That is, one is MOSFET channel length and power supply and threshold voltage. For example, if you look at the 0.25 micron technology, when the gap is source to drain, that length is known as the technology. 0.25 is the length, where the the voltage, the threshold voltage is around 0.6 or 0.5, and the voltage level is 2.5 volt to 3 volt. But if you reduce that length to say 0.13 micron technology, then my threshold voltage goes down to say 0.4 volt, and my power supply VDD becomes 1.3. Immediately you find the advantage of that, because power consumption is VDD square. So with the technology push, you can reduce the power consumption. That's why people are moving from lower threshold region and to higher lower power consumptions, so that effectively you have more integrated circuits at lower power. And if you look at the cutoff frequency, with the reduced length, you are actually increase the frequency of operation, the cutoff frequency. So I told you that initially it starts with 10 gigahertz, then it now 60 gigahertz, but beyond, now it is 120 and 50 gigahertz, even 200 gigahertz has recently been reported. So these are the major the issues in case of MOS devices. Now, if you look at here, how, just to give you a glimpses that how an inductor are actually being placed on the top of that. You know that it's like a mosquito coil, a square type mosquito coils that can actually fabricate it on top of that. And you can have different kind of circular or octagonal kind of structures, and you can actually find out what will be the total length, what is the gap, etc. And then accordingly you will find the Q value of the inductor and the inductor values. Typically for CMOS process, inductor values in terms of nanohenry, you cannot go beyond say 10 nanohenry, or the Q value you cannot achieve beyond 4 or 7. So if you want to get an inductor say around 20 nanohenry, you cannot do it by CMOS. You have to go for an off-chip solution. Or if you want to have say for example a Q value of 200, you cannot achieve by single silicon process. You have to go for an off-chip solution. This is how the bond wire and pads are being modeled. So you know that for a chip, I will show you in a chip that how those wires are actually bonded, and you have to take the model of that. This is how the pad and bond wires are coming. So very recently, you know that this is a very interesting work, that people are trying to develop new concepts in RF design, because you know that I want to design a filter. For example, a GSM band, frequency 915 megahertz fine, and bandwidth is 26 megahertz. Then you need some sort of say a inverse Chebyshev filter of 7th order or 3rd order, depending upon the kind of roll off you want. You have number of components L and C and R, it's pretty high, and it requires lot of areas in the silicon. But by using MEMS technique, micro electromechanical systems, you can reduce the area. This is one such application. You find that 3 such resonators, disk resonators, they are coupled and they vibrate in a particular fashions, and they have a filter characteristics like a band pass filter, and this is the actual image, the same image of those structures. And if you look at the footprint of the devices, it is only 40 micron into 40 micron. So if you look at the LNA and antenna, in between, what is that? This is my band pass filter, and that requires an off-chip solution. But nowadays with the MEMS technique, you can provide an on-chip solutions by using an on-chip MEMS-based resonator, and that is the state of technology of today's RFIC design. And this is the actual structure fabricated and designed here at IIT KGP. And these are the filter characteristics, etc. So now I am quickly going into some of the going one or two more slides I will add. In case of transmitters, what are the parameters are important? What is the power efficiency, modulation efficiency, and the carrier leakage and power consumptions. Carrier leakage means that maybe the carrier will be reflect back from the antenna or from the power amplifier or from the LNA, and it will reflect and mix as an LO, and that will create intermodulation. So carrier leakage is an important phenomenon. And if you look at the receiver, all those selectivity, you know that you have to select a particular channel. Okay, I want to listen to only your voice, not your friend's voice, because all the signals are here. Your mobile phone is actually catching all the signals, but I am only detecting your channels. You know that the tolerance of this frequency selectivity is even few kilohertz, where 2.45 gigahertz is my carrier frequency, where the tolerance level of detective is few kilohertz. The kind of circuit complexity you can think of. Then I also mentioned about the linearity and etc. Then there are different kind of protocol and standard like GSM, Bluetooth and the ZigBee. Bluetooth you know already, but ZigBee is the technology which is recently being adopted for sensor applications and for networking, because in a Bluetooth you cannot have the network. It is one-to-one, but for networking this kind of protocol is 802.11.15.4, which has got three distinct frequency band, 2.4 gigahertz, 915 megahertz, 868 megahertz. So these are the ZigBee, and it's very low power. But only concern to the ZigBee is that it has got low bit rate, that is less than 1 Mbps, that is 250 kbps or 20 kbps low. But sensor applications, that kind of bit rate is enough. So I am quickly going to this. I am showing you some of the now come to the, suppose I want to design an LNA, low noise amplifier I mentioned. Then what will be my design algo? First you have an initial case, then you have to go for a block level specification. Block level specification means that what are the each block. A block means LNA, a mixer, then an oscillators, etc. And then you go into the system level specs, that is your whole cell phone. And then you have an objective specs, that this is my targeted specs. So if you satisfy the block level specs, satisfied your targeted specs, then actually you zeroed down to that value. So you have to, this is iteration, you have to go on doing it and find out the what will be the best design. That means suppose your LNA, you need certain gain, but mixer is giving some attenuation, but noise figure you can actually manage, then you actually reduce little bit of low noise gain, but increase the noise figure or decrease the gain attenuation of my mixer. So this way you have to tailor the intermediate, the cascaded blocks, and to satisfy the overall specification. These are going very quickly. Then I will show you some of the structure if it is here. Yeah, this is one complete die. It is a complete system which is called KGP VCO, that is the first VCO fabricated here at, means designed and using 0.18 micron technology. So you find is a complete die, and on which is a fully on chip solution. Your inductor is there here, and these are the passive components, and these are the pads. Okay, and so internally, so it is, what is the dimension? It is 900 micron into 1200 micron. So roughly 1 millimeter into 1 millimeter area. The whole devices are there, and this is the fast card design. Later on I can show you even a complete receiver designed here is taking that much of, this is the different test. You need huge expertise in understanding the testing, whole board to be tested. This is done in VLSI lab, you can find those. These are how to make a test setup. This is the how to, this is the actual frequency you can find here, exact oscillation at 2.45 gigahertz, and you will be very happy that okay, your device is working. This is actual frequency operating signals. So this way, if you look at another circuits, just I am going. This is another. This is a complete receiver. Not only receiver, also LNA mixer all together, and you can find what is the dimension. 2 millimeter into 2 millimeter, the whole die, and whole receiver. Think of the tomorrow's challenge. The whole transceivers will be in these dimensions. So even you cannot see it, and that will be implanted in my watch with a screen that can be a cell phone, a video streaming, as well as for voice transmissions, data transmissions, and also for Bluetooth. So here I like to end that I look forward for the students to take, some of you should take the challenges of RF design, because these are never ending challenges, and go on, if you go on doing it, then it's manifold, its applications in terms of physics, in terms of technology, in terms of circuit application, in terms of communication, in terms of whatnot. So thank you all for your patience.